So the first type of problem that we're going to go through is kind of that problem in that forward direction, using the molar solubilities that you can find in the lab to actually predict what the KSP value or the solubility product value is going to be. We're going to go through two different examples. So let's start with our first example here. So our first example is going to be dealing with a saturated silver chloride solution. So here, theoretically, if we have a 1 liter saturated silver chloride solution, it contains 0.00192 grams of silver chloride at 25 degrees Celsius. We're asked to calculate both the molar solubility and also the KSP value for silver chloride. Now, knowing that this problem is dealing with solubility, I always like to start off with an equation. Every single problem I like to start off with some sort of an equation to look at. So if this is dealing with solubility, I'm simply going to write a dissociation equation. So here is solid AgCl dissociating into Ag1 plus and Cl1 minus ions. The second thing that really bothers me about this problem is the fact that I was given grams. Now, I've told you before that anytime that you're given grams in a problem, about 99.9% of the time, you're going to need to convert those into moles. This is no exception. I'm going to go ahead and convert that into moles. So I looked up the molar mass of 143.32, converting it into moles, and I find that I have 1.34 times 10 to the negative fifth moles of AgCl. So now I'm primed and ready to go. I also know that I have 1 liter of solution, so I can actually take that moles and convert it into molarity, and that will be the molar solubility. So I'm going to take my 1.34 times 10 to the negative fifth moles, divide it by my 1 liter of solution to make myself a beautiful little molarity. That's the molarity of the AgCl solution. And again, that counts as the molar solubility. This is representative of the amount that will dissolve and dissociate to 100% inside of that solution. All right, so now let's clean up our kind of problem grid here a little bit. So now we know the molar solubility is 1.34 times 10 to the negative fifth. And that is the amount that is dissociating to 100%. So I'm allowed to completely use a little bit of stoichiometry here. If I know that 100% of that is going to dissociate, then I actually know both the concentrations of the silver and the chlorine right now. Both of them would, because of the 1-to-1 molar ratios, would be 1.34 times 10 to the negative fifth molar. That's wonderful. We're one step closer here. Now, also, because of the double-headed arrow, any time that we have an equation that uses that double-headed arrow, you really should be thinking about writing that equilibrium expression. And because this is one is dealing with solubility, we call this one KSP. So the equilibrium expression for this case would be the concentration of the silver times the concentration of the chlorine. I just happen to know both of those values. So at this point, it's a plug and chug style problem. We just take those two values, plug them in, voila, chug back out an answer, 1.8 times 10 to the negative 10th. So I've in fact calculated both things that they wanted. The molar solubility is the molarity of the AgCl. We found that simply by converting our material into moles. And then the KSP value is essentially the K value that comes out of this lovely K calculation. Let's move on to a slightly more difficult example, one where students tend to start to make a little bit of mistakes here. And I think you'll probably pick this up right away. The problem, at least initially, looks almost identical. Again, we have a 1 liter solution. We're given a number of grams. We're asked to calculate both molar solubility and KSP. But this time, the material is calcium fluoride, CaF2. Just like before I get started with anything, I like to have a balanced chemical equation in front of me to look at. In this case, here it is. Calcium fluoride is going to dissociate into calcium and 2 fluorine atoms. Now, there's 2 huge opportunities to kind of go off the rails here. I want to make sure that I highlight both of these to you. But because we're not dealing with 1-to-1 molar ratios exclusively here, there's a pretty big opportunity to kind of make some mistakes. So just like before, I'm given grams. Hate those grams. Let's convert them straight away to moles. So I'm going to take my 0.00167 grams and convert them into moles. The molar mass of the calcium fluoride was 78. I find that I get about 2.14 times 10 to the negative fifth moles. Again, I need molarity. I'm given 1.00 liters. So I'm going to divide those moles by those liters and come up with a molarity. That molarity is, in fact, the molar solubility of the calcium fluoride. That does, in fact, represent 100% of the material that is going to dissociate. So now I can actually assign the concentrations of both the calcium and the fluorine ions. Now there is a 1-to-1 molar ratio between calcium fluoride and calcium. So the concentration of the calcium is going to be exactly the same at 2.14 times 10 to the negative fifth molar. But unfortunately, I have a 1-to-2 molar ratio between calcium fluoride and fluorine. That means my fluorine concentration is going to double. So that, in fact, is going to be 4.28 times 10 to the negative fifth molar. This is the number one area where students tend to make some mistakes. Please do make sure that you take into account those multiple ratios. The AP makers actually know that you're going to stumble on this issue, so they tend to pick examples that have other than 1-to-1 molar ratios here. All right, so now we've accomplished getting the molar solubility. We need to start working on the KSP. Let's define it. We have a double-headed arrow. We really should be writing out our equilibrium expression. So what does that look like? Well, in this case, KSP looks like calcium times fluorine squared. Now again, those coefficients really matter. So again, these coefficients matter now in two places. It not only affects the concentration of the ion, it also affects the math going into the equilibrium expression. So again, notice the squared there. That's how this problem is supremely different. But from here on out, it's just a matter of plug and chug. I plug in those two values. Simply plug in the values for the two concentrations. So the concentration of the calcium, the concentration of fluorine, and it's just time to do a little plug and chug math. So we chug it back out, and I find the final answer is actually 3.92 times 10 to the negative 14th. Not too shabby. So now before we leave this section, I just want to make sure that we understand why do we actually care about this number KSP? Well, one of the very convenient pieces of information that the KSP value can share is essentially which salts are more soluble than one another. Before you actually take that into consideration, it's important to remember that you need to be comparing apples to apples, not apples to oranges. KSP, you can use that to compare the relative solubilities of your ionic salts only if they contain the same number of ions. So for example, I wouldn't want to compare something like AgCl to something like PbCl2. The multiplicative effect of that two chlorines versus one chlorine really kind of messes with that KSP number, and it becomes very hard to directly compare KSP numbers. Now you can directly compare molar solubilities, which is why the next set of calculations is going to come in kind of extremely handy. We're going to convert backwards from KSP back to that molar solubility. But let's look at this example first. So here I have three sets of silver compounds. Again, both of them only have two ions, a cation and an anion. And I have three separate KSP values. Now remember, when a K value is large, it usually is shifting that equilibrium far to the product side. And when a KSP value is small, it's shifting the equilibrium more to the reactant side. In this case, if I'm dealing with solubility, the product side is dissolved and the reactant side is undissolved or precipitated. So the larger the KSP value, like what's indicated here by the AGF, indicates that this equilibrium is actually shifted more toward the product side, and AGF is slightly more soluble than the other compounds. In like manner, the AgBr, with its lower solubility of 3.3 times 10 to the negative 13th, has its equilibrium shifted further toward the reactant side, the precipitate side. So it actually is less soluble.